Welcome to linear approximation. The context here is that we've got some complicated problem that we're trying to solve, and either we can't solve it exactly or it's pretty complicated to do so. And so instead what we're going to do is create a closely related problem that's much more simple and much easier to solve. That's how we'll approximate the solution to the original problem. For example, this could happen if you've got a drone flying around and maybe it's making computations about its location and speed relative to some other objects. You have to strike some kind of balance between how precise you want those calculations to be versus how much computational cost there is, like how much time it takes to make each computation for the computer chip inside the drone or something like that. So for us, we're going to look at a particularly simple type of example of approximation that is really important to understand before you move up to higher level approximations. So let's say we've got some value z that depends on two other values, x and y, and let's say we can write it as z equals f of xy, where f is some function. Then what we're going to be doing is we're going to try to approximate that z value for some x and y value. They're probably just weird x and y values, like let's take x equals 1.2 and y equals 1.9. Then we want to approximate the z value when x is 1.2, z is 1.9. So the first thing that we're going to do is take this complicated curvy surface, that's the graph of z equals f of xy, and we'll find a place somewhere close to the point 1.2, 1.9 where we know the z value. So let's just pretend that we know the z value on that curved surface at x equals 1 and y equals 2. That's pretty close to our original point, and this is a common thing that you need to require for an approximation setup. You have to have some sort of base point from which to make your approximation. So ours is going to be at 1, 2. What we're going to do is take that surface, that curved surface, and make a flat tangent plane at 1, 2. And then when we want to approximate the z value on that curved surface at the point 1.2, 1.9, we'll just calculate the z value on the flat surface at 1.2, 1.9. That will be much easier to calculate in most circumstances, and it should give us a decent approximation to the z value on the curved surface at that point. And of course, if the curved surface is behaving really wildly, then it may not be a great approximation. There are a lot of factors that go into how good the approximation is, but still, this is the method that we're going to use to make our approximation. So let's quickly go over how you make a tangent plane. First of all, we're going to need a normal vector that's normal to the plane to get the equation of the plane. So we'll make two vectors inside the plane and then take their cross product. That gives us the normal vector. So for the first vector in the plane, go 1 unit in the x direction, no units in the y direction, and then as you're going just 1 unit in the x direction, the z value along the plane has to change by whatever the slope is of that plane in the x direction. That slope is just the partial derivative of f with respect to x of your original function, evaluated at that point. For us, the base point is 1, 2. So our first vector will be 1, 0, fx, and then for our second vector, let's do the same thing but in the y direction. So just go 1 unit in the y direction, and the z value has to change up or down by the slope of the tangent line in the y direction. That's fy, so that's 0, 1, fy. And now we can take their cross product, and when you take their cross product, in that first slot, you get 1 times fy minus 0 times fx. In the second slot, you get minus, and then in parentheses, you get 1 times fy minus 0 times fx. and then in the last entry there you get 1 times 1 minus 0 times 0. And now that we have the normal vector, we know that we can take the dot product of that normal vector with any vector in the plane, and that will give us 0 because they're orthogonal vectors. So what we're going to do is take the base point 1, comma 2, comma whatever the z value is there, but we'll call it x naught, y naught, z naught for the general situation. Take the vector from there to any point x, y, z in the plane, and then your components of that vector in the plane are going to be x minus x naught, y minus y naught, z minus z naught. So when you take your dot product and set it equal to 0 to get the equation of the plane, then you get this equation. And we're going to solve for z in this equation because that z value is what we're trying to approximate. Sometimes the z value is called L, so we'll write it as L in a minute. Notice that this z value, this approximation on the tangent plane, just takes the z value at the base point, so that's the z naught, and then it either adds or subtracts a little bit as you go in the x direction, and then it adds or subtracts a little bit from the z value as you go in the y direction. So take the z naught and then add slope in the x direction times change in x plus slope in the y direction times change in y. That gives you your final z value on the tangent plane, and that is the approximation to the z value on that curved surface. So let's go ahead and work out an example. Here's our example, and so we need to take the partial derivatives with respect to x and y. For fx, treat y as a constant, so we'll get 2 minus 0 plus 4y. And then for the partial with respect to y, treat x as a constant, you get minus 5 plus 4x. We want these slopes at the specific point x equals 1, y equals 2, so they should give us numbers. So plug in x equals 1, y equals 2, and for fx we get 2 plus 8 is 10, and for fy we get negative 5 plus 4 is negative 1. So now we have the equation of the tangent plane almost. We have the fx and the fy. We have x naught and y naught. Let's get z naught. So plug in x equals 1, y equals 2 into the original equation, and we get 2 times 1 is 2 minus 10, so 2 minus 10 is negative 8, plus 8 is 0, so z naught in this case is 0. So our linearization, which again people sometimes write as L, they sometimes write it as L of x, y, to emphasize that it depends on x and y. This is what it is in this case. No matter what it is, no matter what your partial derivatives were, you find numbers for those partial derivatives, and this thing always turns into a linear equation. So the original value, the original function in our simple example is not that challenging, but it could have trig functions in it, rational functions, logarithmic, exponential, any powers of x. So changing that into a linear function makes it so much easier to calculate. So now the value that we were actually trying to approximate was f of 1.2 comma 1.9. And to do that, we're plugging in those values of x and y into this linearization. So you get 10 times, and then you'll get 0.2 when you do 1.2 minus 1. So 10 times 0.2 is 2. And then for the next term, you have minus 1 times negative 0.1. So that's a plus 0.1. So 2.1 is our approximation to the z value on the curved surface by taking the z value on the tangent plane. Once you have this set up, we can make approximations for other points that are close to x equals 1, y equals 2 very easily. So let's go ahead and do this for 0.7 comma 2.2. If you plug these numbers in, you get 10 times negative 0.3, so that's negative 3. And then you get negative 1 times 0.2. So minus 3 minus 0.2 is negative 3.2. And we can do this for any point we want that's reasonably close to x equals 1 and y equals 2. This is the idea of linear approximation. You take something that's challenging, you take this difficult, in our case we could visualize it as a curved surface. If you have more variables, you can't visualize it as nicely, but it's the same concept. You got some complicated function, you just turn it into a linear function using some sort of tangent space, a tangent plane here, and then your calculations become very simple.